Hi everyone, myself Dr. Arun. Today we are going to discuss about FM faster seeley discriminator. It is the one of the type of FM detector or demodulator. So this is also called as phase discriminator. So now we are going to entering into the video. So FM balanced slope detector. Before discussing faster seeley discriminator, we have to identify what is the major disadvantage in the balanced slope detector, how we are eliminating that particular disadvantages by using faster seeley discriminator, that we are going to discuss. So you can see here the balanced slope detector, the major issue is the three tuned circuits are available. The first tuned circuit is tuned to FC, the second tuned circuit is tuned to FC plus del F, and the third tuned circuit is tuned to FC minus del F. So while aligning this particular tuning, it is very difficult to adjust exactly to get the very good output. So this is the one issue in the balanced slope detector. This particular problem is eliminated by using faster seeley discriminator. By performing this particular changes, we are increasing the linearity also. So in the balanced slope detector, the linearity is less compared with faster seeley discriminator. So you can see in the block diagram, in the circuit diagram of faster seeley discriminator, we can identify what is the exact difference. So here we can see the corresponding two tuned circuits only available. Both the tuned circuits are tuned to FC. So there is no FC plus del F and FC minus del F is there. The primary, secondary both are tuned to FC. So this is the main difference. Another one is in the primary side is directly connected to secondary through the coupling capacitor CP. So this is the another modification we did to improve the linearity in the faster seeley discriminator. So before discussing faster seeley discriminator, what is the basic principle behind the faster seeley discriminator? Here we are specifying the phase discriminator. The balanced slope detector is coming under frequency discriminator, but in the corresponding faster seeley discriminator we are specifying as phase discriminator. So here in the phase shift between the primary and the secondary voltage of the transformer is a function of frequency. Whenever the frequency varies, the corresponding frequency variations will be represented in terms of phase variation in the faster seeley discriminator. The primary and secondary windings are both tuned to center frequency, already we are mentioned. So here we are achieving the better linearity than slope detector. So in this particular circuit diagram, as like balanced slope detector, here also the two slope detectors available, slope detector 1 and slope detector 2 is available. And also we can apply the frequency modulated signal at the input side. We are expecting the message as a demodulated signal at the output side. So the entire response or characteristics of this faster seeley discriminator is represented as S-shaped curve. So the center frequency we are representing as FC. The upper side we are representing FC plus del F and the lower side FC minus del F. So whenever the frequency increases, the output current will increase or output voltage will increase. Whenever the frequency reduces, the output voltage will decrease. So automatically we are able to get a positive cycle and also negative cycle by using faster seeley discriminator. Here this particular diagram representing the Phasor diagram of faster seeley discriminator. So V12 and 1 by 2 VBA, this is representing V12 is called primary voltage and 1 by 2 VBA representing secondary voltage. So there is a phase difference between primary and secondary voltage. This will be decided based on the input frequency. If the input frequency is equal to carrier frequency, exactly equal to the carrier frequency, here 90° out of phase between primary voltage and secondary voltage. Suppose if the input frequency is higher than carrier frequency like Fc plus del F. In that particular case, less than 90 degree. You can see the primary voltage is here and the secondary voltage is here. The phase difference between the primary and secondary is less than 90 degree. The final one is if the input is below carrier frequency, suppose Fc plus minus del F, in that particular situation, the phase difference between primary and secondary is greater than 90 degree. So 90 plus theta, greater than 90 degree. So here why we are representing this particular Phasor diagrams means, here we have to calculate what is the net potential across diode D1 and diode D2. So the net potential across diode D1 is represented as VA0 and diode D is VB0. Based on this length of the vector, we are deciding how much potential across the diode D1 and D2. So the D1 potential is calculated by using the equation D1 equal to V1 plus 1 by 2 V2 or 0.5 V2. Similar manner here VB2 is equal to V1 minus 0.5 V2. So here why they are adding this V1 means the primary voltage is directly connected to your secondary, and also because of mutual induction of the signal in this particular transformer, you will get 1 by 2 V2 and 1 by 2 V2. So because of this center tapped transformer, we will get a 1 by 2 V2 and 1 by 2 V2. So now this entire Phasor discriminator we are going to discuss by using three different modes of operation based on the input frequency. How we are getting the message signal. So here the first mode of operation, I am considering the input frequency is equivalent to carrier frequency. So here we are going to apply the input frequency is equivalent to carrier frequency. Both the tuned circuits are tuned to carrier frequency alone. Both are in the resonant condition. The secondary of the transformer give the equal response because it is already tuned to carrier frequency. So now at the carrier frequency, VD1 and VD2 are equal. Both the potentials across diode D1 and D2 both are equal. Hence the net output of the discriminator will be 0. If the potential across D1 and D2 is equal, due to that corresponding slope detector 1, based on the input signal, the net output is V01 and V02 both are equal. Here we are mentioned as plus 5 and minus 5. So this potential is equal means the net output is difference between V01 and V02. The net output we are consider as 0. So now based on this Phasor diagram, the primary voltage and the secondary voltage, the resultant potential, the vector size decides the potential across the diode D1 and also D2. Here both the vector size are equal. We are assuming both the voltages across D1 and D2 are equal. Obviously the net output is 0 because both will generate equal magnitude and opposite in polarity. The net output is 0. So now we are moving to mode 2 operation. Here the input frequency I am considering Fc plus del F. So Fc plus del F means higher frequency, so 100 plus 75 kilohertz. As the carrier moves off to one side of the center frequency, that means above Fc or below Fc, the balance condition is destroyed. One diode conducts more than other. So this results the voltage across one of the resistor being larger than other. So whenever the balance condition failures, one diode will conduct more, the another diode will conduct less. The net output voltage depends on the corresponding potential across R1 and R2. Based on that, the polarity of the output voltage will be decided. So in the second mode of operation, the input frequency is Fc plus del F. In this particular situation, when the input frequency increases above the carrier frequency, the phase shift between primary and secondary is reduced. You can see minus 90 degree, 90 degree minus theta. So less than 90 degree we are achieving. The resultant potential, you can see the very important point, length of the vector decides the potential across the diode. You can see here the length of the vector of VA0 is higher than the length of the vector of VB0. So I can conclude VA0 is higher voltage compared with VB0, then potential across D1 is more compared with diode D2, the net output voltage is positive voltage. So here VD1 is greater than VD2, hence the resultant output will be, I am considered as plus 8 and minus 3, the resultant output is positive voltage. So this is the operation of if you are applying input frequency signal is above carrier frequency. Similar manner, the third mode of operation, here I am applying the carrier frequency or input frequency is less than carrier frequency. The input frequency is less than carrier frequency, Fc minus del F. Obviously this will appear due to negative cycle of the message signal at the transmitter side. So when you are applying this low frequency signal to frequency demodulator, then when the input frequency is reduced below Fc, the phase shift between V1 and V2, that means primary and secondary voltage, increases. Then you can see here V12 representing primary voltage and 1 by 2 VBA representing secondary voltage. The phase difference is greater than 90 degree. In this particular situation, you can measure the length of the vector VA0 is small compared to VB0. Obviously, we can say the potential across diode D1 is less, diode D2 is more. So whenever the potential across diode D1 is less and potential across diode D2 is more, this diode D2 will conduct more and it will releases maximum current. Then the potential across R4 is maximum compared with R3. Then the resultant potential is minus voltage or negative. So plus 3 minus 8, the net output voltage is minus 5. So we are generating both positive cycle and also negative cycle based on the frequency variation in the frequency modulator input signal. Whatever may be the frequency variation present in FM, that will be converted as amplitude variation. So by using Phasor discriminator. So in this Phasor discriminator also having some advantages and disadvantages. The first advantages offers good level of linearity, simple to construct using discrete components, provides higher output than ratio detector, provides more linearity output, that is low distortion than ratio detector. Disadvantages: high cost of transformer, narrow bandwidth than ratio detector. The circuit is sensitive to both frequency and amplitude and therefore needs a limiter before it to remove the amplitude variation and hence amplitude noise. So based on the final point, if any amplitude variation present in the input of the frequency modulated signal, that amplitude variations are not eliminated in Phasor discriminator. That's why we need additional circuit called amplitude limiter that will be implemented before FM detector. Then only we can improve the performance of the corresponding detector. So this is the entire operation of a Phasor discriminator. So thank you all for watching this video. So if you like this video, so kindly comment and share. Thank you all. We will meet again with other video. Thank you.